Welcome to the Breaking Ground track. If you are not here for the Breaking Ground track, you are in the wrong place. Or maybe you are just here because you work for the NSA and you are interested in what's going on. We have the NSA Playset being presented by Michael Leibowitz. Michael, who is known as Rootkiller on Twitter, has done a hard time in real time. An old-school computer engineer by education, he spends his days championing product security for a large semiconductor company that shall remain nameless. Previously, he developed and tested embedded hardware and software. That's got to be bad kerning. Clicked around with strap-on boot ROMs, mobile apps, office suites, and written some secure software. Which is quite an accomplishment. On nights and weekends, he hacks on electronics, writes B-sides CFPs, and contributes to the NSA Playset. So let's see what it's all about. Put your hands together for Michael Leibowitz.
Hello, hello. All right, so this is the NSA Playset bridging the Airgap without radios. And as I think he just said, I'm Michael Leibowitz, and it's more or less what he said. My day job is in product security, and then the rest of the time I food around with electronics. I work for a large multinational corporation that I won't name, but you can probably figure out. And of course, what I say here is not the words of my employer or the views of my employer. Don't be confused. So let's talk about the Ant catalog. The Ant catalog is a literal catalog that the NSA makes from their tailored access operations group, and basically it is a catalog that other government agencies can buy from to purchase malicious implants or software to exploit bad people or hackers, or basically you and I. And this was leaked in 2013, I think, something like that. And so this is an example of one item. You can look at the whole catalog. There's a bunch of different things with funny names. Each one has a funny name, a sort of description of what it is. In this case, it is a listening device. That if you haven't seen Mike Osman's retroreflector talk, you really should. This is a active retroreflector. And I think that what is most amusing about the Ant catalog is, like any real catalog, there's a price at the bottom, right? There it is, $30, which is a pretty good deal. A lot of the Ant catalog stuff is kind of expensive. And so, the NSA Playset is like, well, why should they have all the fun? So we're basically recreating and re-envisioning the tools of the Ant catalog in an open way, whereas they do it in secret. We do it in the open, and we try to make things easy to use and easy to learn from, and hopefully this makes the world a more secure place, or at least hackers to have more fun. And we have a website, and this one isn't updated, but this project is on the website, but I haven't updated the information yet. So last year, Josh Datko presented Chuckwagon, and Chuckwagon is a implementation, or a sort of parallel implementation of the WagonBed platform. And the WagonBed platform is a platform that is not a Ant catalog entry, but several of the Ant catalog items say that they support WagonBed hardware. And basically, the WagonBed hardware is a series of hardware implants that they put into a computer, and it talks over, in this case, I2C back to the infected computer, and then forms some sort of out-of-band network for command and control purposes. And so, in this case, it uses a BeagleBone, and the I2C bridge is over VGA. And it uses a GSM modem for the out-of-band radio. And If you haven't seen Josh's talk from last year's DEF CON, you should. It's also pretty good. While I wasn't thinking about the Ant catalog, I was thinking about the Internet of Things and how funny the Internet of Things was, and how it's going to be really hilarious to have a whole bunch of small devices with tiny TCP/IP stacks in them that were written yesterday, and billions of them. My company was also really interested in the Internet of Things, and so last year at CES, or maybe it was the year before, he got on stage and he demoed a smart shirt. It was a shirt with electronics in it, and I don't know, I didn't really watch the demo, but it said smart shirt and Internet of Things, and I thought, that's freaking hilarious. And I thought, okay, well, before we get into that, let's talk about the Internet of Things and radios and radio technology. And so I know this talk is without radios, but a lot of the Internet of Things is built upon 6LoWPAN and or 802.15.4, and I think that there's a lot of confusion about what that is and how and what that means, and I'll tie that back into this in a few moments. But so there's LoWPAN, and then there's 6LoWPAN, but the traditional radio topologies for these low power networks doesn't really work because these devices are supposed to be powered on with a watch battery for months or years, and so it turns out that the traditional network topology that we use, or networking techniques that we use for, say, like Wi-Fi, don't really work in that situation. So what they basically do is they do scheduled transmission, because it turns out that the reception is more power expensive than the reception. And so they communicate in short bursts, and but the radios aren't very powerful. So how does this work? How do you get a large moat of operation of nodes? So maybe one can only reach a few, but the other can't be reached. So we need a mechanism to communicate node to node. We need mesh networking, where we can go from node to node to node to node, and finally to node. So this is sort of a B-Sides to B-Sides talk. So for Portland B-Sides last year, I saw this internet shirt that our CEO had made, and I thought, well, that's silly. We should make internet hats. We could make thinking caps, and we should make them for B-Sides. I don't know if you can see it, but there's a tiny little B-Sides logo there. It turns out it's hard to make a circuit board that will fit on a hat that doesn't bend. And so I made, in collaboration with Joe Fitz, I made these badges, and we decided what does it mean to have an internet hat? Obviously, it should do some thinking for you, but really wanted to turn this into a game for B-Side, so it would be like a laser tag game. You push the button, you zap a hacker. But then that became sort of a question, like each node would have an IPv6 address, and which hacker am I zapping? I don't know. Is it that guy? Is that guy? I don't know your IPv6 address. So we thought, okay, we need to zap that very particular hacker. And so I got some cheap infrared LEDs and the consumer infrared, these little photo transistors, just like they used in television remote controls, and put them on the board. And this is a hacker conference, so I couldn't just be like laser tag, like boom boom, you're zapped. It had to be something a little more clever. Otherwise someone would just come in and zap everybody. So I thought, okay, well, how are we going to do this? So it'll send a zap with a nonce, and then the other guy will reply with another thing, and then it will all go together. And now I need to have like data transfer, because with the remote control, it just like sprays. It's just like, okay, channel up, and then the TV says, okay, you probably didn't just hit it 3 times 10 milliseconds. So I'll just take one of those. But that wasn't going to work for us. So what I did is I made a little tiny packet system. It sends a few bytes. It has a little packet in it with like a message you've been zapped, who zapped you, and the knots. And when I first tried this out, the thing that struck me was that the range was really spectacular. Like I wanted it to be, from one seat to the next, like zap, zap. But it was more like from one seat in the back to zapping everyone in the room. And I was like, wow, that's amazing. And then I started thinking, like, maybe I don't need this IPv6 radio at all. Maybe I can do this all with, some fancy infrared. And I thought, maybe this could be a really neat way to devise a hardware implant. This is pretty small. I could probably make it a little smaller, and then we could and then we could add this to the playset. And so I dreamt up this idea. So I said, okay, so here's the way it works. I get the hacker, and he delivers the hacks to the victim. But this time, we want to deliver the hacks without radios. And, to some extent, this may seem a little bit like a hat trick. But, there are they're what I call radio hostile places, or either heavily monitored radio places where new networks are detected and monitored. There are companies out there that make little SDR products, which, you can put in your server room and make sure that the radios that it sees are consistent with a pattern of normal use, presumably to detect things like a chuck wagon implant or similar with an orthogonal radio. And then there are places, of course, that are like, where radio waves just don't go well, like there's no cell reception, deep underground, like Stuxnet or something like that, where the Airgap was, where the Airgap was jumped. And I couldn't think of, I didn't have any sort of imagery of, an underground nuclear facility, but this was kind of as close as I could get to convey, I think, the same idea. So basically what we want to do is we want to, we don't want to be right there delivering the hacks, because that sounds scary. We could get caught. We want to deliver the hacks through the tubes to an implanted machine that then relays our hacks from node to node to node, much like the mesh networking, to go to span a long distance with a mesh network. And so, obviously this requires each node to be implanted, but that might not be actually that difficult if you think about it. So, let's talk about VGA. This image I thought was absolutely hilarious because I don't know if you guys can see it, but the little dots, the little arrows that tell you what wire is what, just tell you what color it is. So this one really just says blue, and then this one says small red. That was tremendously helpful. And if you look at VGA pinouts around, if you just sort of randomly look for them, there's so many. Okay, there's red, green, and blue, and then there's H-sync and V-sync, which basically, if you don't have that, nothing works at all. And then there's these other stuff, and here they're okay, that's all ground, or these are reserved, or they're not connected, or they're not used, or they're deprecated, or whatever. But actually, there's an ITC bus that goes through there, and this is something that happens in VGA. This is something that is present in DVI and in HDMI, and it's just keeps going and going. And basically, when you plug your computer into a monitor, and it knows okay, this is a monitor, and what kind of resolutions and modes the monitor supports, and the size, there's a little PROM in there. There's a little PROM, somewhere in your monitor, and that's the DDC PROM. And basically, you read this formatted information, which calls EDID. The computer reads this information called EDID, and then it parses this block, and then that's how it decides what to do. Usually it's the kernel or some pretty low-level component that does this parsing, which is, nothing could go wrong there. There were, I think, a few years ago, some good bugs found through fuzzing of EDID, and my favorite is my size is -1. And so ITC is I talked about ITC before, but what is ITC? ITC is, or sometimes called a two-wire bus, basically, is literally 2 wires, and ITC is underrated, I think, but is a multi-master, multi-slave bus. So essentially, you can have, one master. So in this case, the VGA adapter is the master, and then there's the DDC prom, which is the slave. And then, you're free to hook up other things there. So, there's like, maybe like a malicious implant in there, and it can be either master or slave. Now, this topology looks a little wonky because if the host is the master and the implant is the master and the DDC is the only slave, then there's really no fun that can be had. But actually, if you just go poking around on the ITC bus of your display adapter, you'll see like a few different things there. Inside the monitor, or inside, or if you have a display adapter, you can see things inside there, and they will happily take commands from you. And ITC is also interesting in that ITC has destructive collision or non-destructive collisions. So if you want to be the DDC prom and say, like, my size is -1, and there is a DDC prom already, basically whoever says 0 first when the other guy says 1 wins, and the other guy will shut up. So all you have to do is say 0 earlier in the EDID struct than he does, and you get to control what the EDID struct says. So let's talk about CIR, consumer infrared. So I alluded to earlier how consumer infrared works, how IR remote controls work. Basically, they have a modulated signal, and this signal is modulated usually about 38 kilohertz. And then you can see here there's the modulated signal. It goes burp, 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 burp. And then the receiver automatically demodulates that and turns it back into normal wave. And the graphic looks kind of weird because I ripped it off and inverted it and didn't clean it up well. And so one of the things about the differences between consumer infrared and IRDA, the infrared data something. So a while back, before Wi-Fi became popular, there was something called IRDA. There was an IRDA consortium, and people put little LEDs and receivers in laptops and calculators and crap. And it could go like 4 megabaud, and you could like put the computers next to each other and send crap, and it was cool. And one of the things that I first looked at when doing this was like, well, I should just do this with IRDA because that's fast and good for data transfer. And one of the things that IRDA was, the trade-off for IRDA was that they made it such that range was not very good. So it's designed to hit something very specific at a short range. You don't want to be like blasting bytes to everybody in the room, but TV remote controls do. They want to send, off walls, off ceilings, and send to something that's far away. And so that's why I went with consumer infrared, although there was somewhat of a trade-off in terms of bandwidth, which we'll talk about later. So then there's serial communication. And so this is the UART format, and I don't know how many of you are familiar with this, so I'll just sort of go through it real quick. So the A is for asynchronous, U is for universal. Basically, you can connect 2 computers that are different together, and they don't have to share a clock. This is great because R2 our two infrared devices also don't share a clock. And this allows us, by encoding a serial protocol, to synchronize the UARTs together. And basically, there's a start bit, there are data bits, and there's optionally a stop bit. It's not too exciting. And then when you modulate it together with the 38 kilohertz signal, so here it is from my logic analyzer, you can see basically the modulated data on the top, and then the received demodulated data and the decoded data. So the sort of interesting thing about this, if you look at the previous slide, is that the idle state is up. And then in this slide, the idle state is down. So you have to invert the transmit in order, and the receiver will invert the reception. The reason you have to do that is if you leave idle high and you're encoding all the time, you're just spraying nonsense everywhere and nothing else can communicate. But this leads to an interesting problem. So this is sort of another picture of the UART encoding, but and what you can see is there's the bits 1101, 001, and then 0. What happens if you make all the data bits 0? Then you just have basically the start bit and then 7 bits or 8 bits of silence. So you have the start bit, 7 bits of silence, start bit, 7 bits of silence. It turns out that, and this is a problem that radios sometimes share too, there's been a problem in radios, is that if you are transmitting with long delays, you lose synchronization between them. And this is something that I have somewhat struggled with. There are a number of different techniques to avoid this. So one is you can do bit stuffing. Every n number of bits you stuff a 1, or you can do byte stuffing, n number of bytes you stuff a non-zero, or you can do flags like HDLC, where like if you say this number of zeros in a row, I actually give you all 1s, but if you want that, then there's an escape. And so I use byte stuffing, but it kind of works and kind of doesn't work. But then I discovered if you just compressed all the data, you have very few zeros. So this is basically the underlying packet format. So basically this works like a MAC and then a higher level. So basically you have the implant running the MAC, and then it transmits the packets and manages the communication channel, and then you have the software on the host that kind of processes that and like does stuff. So there's a 128-byte packet, and so we have a source, a destination, a type, and then hops, which I'll talk about in a moment, and then stuff and a CRC. So, and it's a 16-bit CRC, so you kind of know that you've got something that probably wasn't corrupted. But the world is a kind of noisy place. And one of the things about this is you're constantly kind of receiving spurious garbage. And again, radios have the same sort of trouble. So basically, the receive apparatus has a sort of guard sequence that if you don't output that, it decides this is just random garbage. And then once you pass that, it decides, okay, we're now receiving a packet, and there's a leader to establish synchronization. And then, but how do we do this meshing? So in 6LoWPAN, it's really complicated. There's neighbor discovery, and then there's the sort of optimal route calculation, and then there's different choosing different kinds of routes to avoid congestion, and some radios have coordinator roles and that coordinate this, and some radios don't. And I didn't do any of that. So basically, there's a flag for hops in the struct. There's a 4 bits for that. And if this packet is not for me and it's less than 15 hops, okay, we'll just increment the hops and send it along. This is like more or less the approach. There's actually a naive bug in this approach that if you have 2 things right next to each other, they both reply at the same time and obliterate each other's transmissions. So you wait a random amount of time. This is kind of similar to Ethernet, actually. You wait a random amount of time, and then you transmit. And if someone else has transmitted that hop before you, you basically give up and say, well, someone else did it. So I wanted to make a easy to use playsetable. I made a word. I wanted to make a easy to use hardware and software platform that I could hand over to people such as yourselves to start hacking on it and playing with it. It had to be, small, cheap, easy, fun, and I guess corollary to cheap was widely available. And I chose a AVR platform, which you may seem familiar to you from there in the Arduino platform. And the Arduino platform is definitely easy. It's apparently so easy the kids can do it. A lot of people look down their nose at Arduino, and I kind of looked down my nose at Arduino for a long time, but actually Arduino is pretty great because really it's GCC, C++, and a library that works pretty okay, and if you don't like it, you can throw it out. So I think that when you look at how to use Arduino, this is kind of what you expect to see. But actually, you can really just use, make, install, all these sort of tools like a real hacker and a real editor. You don't have to do that. So let's talk about the hardware. So the hardware needs to be really small. In fact, this is a good time to show how small the hardware ought to be. So basically the idea is to put it inside a VGA connector. So one like this, and with a VGA cable hooked up to it, and in there, this one is closed up with wires sticking out instead of VGA cable. And it's got to have room for the VGA guts plus a tiny little circuit board that's like this big, which you can't see, but that's kind of the point. It's little. So I needed something to be fairly simple so that I could make it small. And basically, this is as simple as I could get it, and perhaps no simpler. In fact, I made it a little too simple with the first iteration, and that bit me in the ass, so I made a second iteration. So there's the microcontroller over here. You can see my mouse moving. Oh, good. There's the microcontroller over here, the ATmega 328, the crystal, the receiver, a transmitter, and a big fat LED, and then a 2 megabit PROM so that you can stage downloads or uploads or exploits. And then I made a board. And the first board, this isn't the first board I made. The first board I made was really, really tiny. And I discovered it was really hard to work with a really, really tiny board. So a friend of mine said, "You're a dumbass, just make it bigger and then cut it in half when you're done." So I took his advice. And so basically there's the microcontroller, there's a capacitor, the receiver, the LED, and some other garbage. This is where you hook it up to the VGA port. And then the debug connectors for making things nice and easy, and a bunch of blinking lights. And then the green part, that's the part where you cut it in half. And when you're ready to implant it. So the idea is that it's easy to play with. So there's one that's ready to be played with. You can hook it up to the in-circuit programmer. It has a little UART connector like Arduinos do, and you can talk to it, and etc. And then there's a jumper here for I2C. And then, and that's neat. And you know, they're like this big in reality. And then you cut off this part here, and then they become, you know, as big as that one I showed earlier. And basically, this fits damn near exactly into the shell for the VGA connector. And then you plug it into your computer, and then you have fun. So before I get to that, and when I say fun, sometimes it's fun, sometimes it's really frustrating. It turns out that when you when you goof around on the I2C bus, some VGA controllers are like, I'm not going to talk to you anymore. I'm going to turn this bus off, and then you have to reboot the computer, and that kind of sucks. So what is a Faraday cage? So I wanted to show, like, you know, this goes through, without radio waves, goes through radio denied areas. And so I made a Faraday cage which blocks all of the radio communication in or out. And I thought this was a great idea. And then I realized that my connection to this is over Wi-Fi, which means I'm stupid. So I have my little tiny Faraday cage which I built out of like picture frames and copper sheets I got on Amazon. And you know, like 1 a.m. last night, everything like was basically working. And then like by 7 a.m., nothing freaking worked anymore. So, oh, and also your TV, if you're in the Tuscany, the monitor, the TV in your hotel room will respond to I2C, but you cannot get it to display, but you can still fruit with the ROM on it. So I have a computer in here. I guess you can't see that. I have the Whopper. You know, a computer in a hardened radio place, deep underground, controlling nuclear missiles or something. And then I have, this is my breadboard version because remember I told you before nothing worked. And it hooks up over the VGA port and you can talk to it. Of course I can't talk over that VGA port because I'm using it. But that's okay because I can talk to it over I2C as well, or over USB as well. So this is the Faraday cage, and I expect some people in the back can't see that, so I took a picture of it in my hotel room. But what if you want to go, like, what if it's not like, you know, going between like two things that are kind of next to each other, or a string of things like deep underground in some secret facility? What if you just want to go like from, you know, the parking lot to the victim? And so in that case, you use lasers. And it turns out you can shine a dot on the ceiling through a window, and you can flash the laser pretty fast. You can flash, if you buy one that can flash, they basically sell in two ways in this sort of laser, the 5 kilohertz one and the 100 kilohertz one. You want the 100 kilohertz one. And then you flash it at 38 kilohertz, and you can receive, it projects a ever-widening dot on the ceiling at a fairly high intensity, and you can go pretty long distance with it. And then you need a telescope on the other side. So yeah, you know, with frickin' lasers. Okay, so this is the part where I attempt to demo. I attempt to demo to a computer in a Faraday cage connected over Wi-Fi. So let's see if that works. So I have like 2 lids open. Make sure I'm running the screen. Uh-oh. Oh, I can't type. Tor slow. Hey, okay. Or slow. This is like the time where like people laugh at me and say like, you should have had this set up beforehand. But those people are wrong. No, we'll just do it right here. Okay, so here we're communicating with the with this device, and we can ORP. And so this is sort of ping pong test code, so you can send packets. And there it sent a packet, and then on this side I can do and so this is going to be a challenge because the ceilings in here are kind of a lot higher than they are like in a normal office or in my hotel room or other places. So oh, that's really lame. All right, let's point it downward. And then packets are relaying, and I sent it from this one to another one that isn't it, so it's like basically they're ping-ponging it back and forth. And you can see there, it got to hop 15, too many hops, and it eats it. Well, okay, so that was cool. So now, let's see if we can do this through the Faraday cage. Indeed. And this is like the, okay, let's see if we can make the Faraday cage stay together. I may have to hold it in place. All right. Oh. Okay, just don't touch it. If nobody touches it, should be fine. And then if any luck, like nothing happens. Oh my God, something happens. We got a gap in the Faraday cage. The signals are leaking through. Tor can get through. Jesus. That's lame. But we can turn the Wi-Fi off. Let's see. Shit, I can't turn the Wi-Fi off and switch to the other window. All right. Well, okay. We're in a Faraday cage and pretend like radio waves don't go through. Oh, wait. Aha. I know how to do this. It's tethered to my phone. I can fix it. All right, you just turn the phone into airplane mode, and then at least it's in a radio-denied place. Airplane mode, okay. So now, right. But here we are over here, and then, yikes, angly bits. And so, like from here to here, let's see if it works. Nope, but if I aim it downward, which is pretty lame. And I can't type. Wow. Yay! Okay, everyone clap. We're sending these data through the Faraday cage, which isn't a good Faraday cage, but I turned off the radio so they can't talk anyway. And so that's sort of my test code, and I have a command and control console that it works, but something else doesn't work, and I'm not sure what that is, but basically what? Oh, it's saying you can't find the device. Well, anyway, that demo failed. But basically, I have a utility, and you could say run a remote command, and then the implant side waits for the remote command, and it sends back an acknowledgement, and then it streams all the data back like a CNC console you think should work. And then I'm working on the part where I send and receive files back and forth, but sort of the cool part about this is it does do it over the mesh transport, so I can like do it to multiple computers, and which works in the lab. I have a layer that I can build in there for reliable transmission. So this transmission is not like TCP. It's not like reliable. If a packet goes missing, a packet goes missing, which would really suck if you're like grabbing their company confidential data and then like the first part that you desperately need is missing. So it turns out that implementing reliable transmission is not that hard because you can basically do the exact same thing that 6LoWPAN is doing. You can fragment the IPv6 packet up into 128 byte subpackets, and then you can build a sequence number around that, and then you can build up an IPv6 interface through that. And so that's sort of, well, unfucking all this, and then that's sort of the next step is to build it such that it is a orthogonal IPv6 thing, so then I can have, the Internet of Implanted Things. So that's the show. If you have questions, I'll do my best to answer them.
Will you unmute the mic?
Or if
you have questions, we have Mike set up here in the middle.
Then I can sleep and drink beer.
It's the red one there. Yeah. Number 4. Oh, come on. There was like a Faraday cage bee hive of death, and we have no questions?
There are no bees in the Faraday cage anymore. All right.
Well, thank you very much.
Thank you.
All right, please pick up on your way out if you're leaving. And our next talk is not scheduled until